Hello everyone, this is Samita Gupta. Welcome you all for my 37 lecture of Electronic Devices Circuits, that is current source, and this is my last lecture of this series. So outlines are need of current sources, two transistor current source using BJT, then using MOSFET, then we will do some derivation and then one numerical. So first of all, what is the need of current source? Why we need the current source? Okay. So reasons is we want a fixed, stable, constant current. Then we need current source. Okay. And if we want whatever your current, that should be independent of load or voltage. So that's why we need the current source. Okay. We want set, stable, fixed current, and we want it should be independent of load or voltage. Okay. Now, two transistors current source, or we can say it's current mirror using BJT. Okay. See here, this is your BJT with ideal current source biasing. Okay, in the left side and the right side is two transistors current source, and it is also called as current mirror. What do you mean by current mirror? Current mirror. Mirror means exactly same thing. Means whatever current flowing in this part, that should be same. Whatever current flowing in this part, that is I reference, that same current should be flow in this part. That is called current mirror. Current mirror means exactly replica, exactly same. So whatever current flowing here, that should be same here. Further in the derivation, we will look how it is possible. Okay. So this is basic two transistors current source. Okay. And the third part, there are two transistor current source, but we have attached one resistance, reference resistance R1. Okay. Remember in the configuration, the collector of the transistor connect to the base of both transistors. Okay. Remember, this is the main point for the current mirror. The collector of one transistor should connect to the base of the two transistors. Okay. Now we'll see the derivation, how to calculate the currency. First of all, I reference. Okay. So we'll take one KVL equation in the left side. What is the KVL equation? V positive minus VB1. Okay, see here. V positive minus VBE1 minus V negative. Okay, and one is, if you look this third one circuit, there is resistance R1. Here is no resistance, here the resistance R1. So there is one voltage drop across this resistance R1. So equation will be V positive, wait a minute, I'm writing here. The equation will be V positive minus I reference into R1 minus VBE1, or two you can write anything because these two are identical transistors, minus of V negative equals to 0. Sorry. So from this equation you can calculate the I reference. Understood? From the last equation, from this equation you can calculate I reference equals to V positive minus VB minus V negative divided by R1. This is your equation 1. Okay. Now what is I reference? Okay. Now see, what is I reference? If you look at here, this is your I reference. I reference divided in this two part. One part is on the left side and one part is on the right side. What is the left side? It is a collector. So left side is IC1, right? Very good. And what is in right side? In the right side, it is again two parts. One at the base of Q1, one at the base of Q2. It will be I1 plus IB2. Again, listen carefully. We are calculating the current in this part, that is I reference, and that I reference is divided in two directions. One is at the collector of Q1, that is IC1. One is at the base of both transistors, that is IB1, IB2. So I reference equals to IC1 plus IB1 plus IB2. Okay, since we have taken two identical transistors, if two transistors are identical, then both base current will be equal. So IB1 plus IB2 we can write either it 2IB1 or 2IB2. That depends on you. Okay. Now, if you remember the relation between IC and IB, that is the standard formula IC equals to beta IB. Okay. So at the place of IB, we can write IC by beta. So we have put this equation I reference equals to IC. Same thing, IC1 can also equals to IC2 because both transistors are identical. So IC1 you can write IC2. Okay. Why we put IC2? Why not IC1? Because I reference the current in the one this transistor. So we want to calculate this current because we want to know the I naught. So for I naught we want IC2. That's why convert everything in terms of 2, IC2. Okay, because I reference in the one part we have already calculated. But now we want to calculate I naught. Okay, then we will see both are same or not because it's a current mirror. Okay. So IC1 replaced by IC2 and IB2 replaced by IC2 by beta. Now take common IC2. So it is IC2 1 plus 2 by beta. Now IC2 from this equation will be I reference upon 1 plus 2 by beta, and that IC2 equals to I naught. Okay. Now you will see IC2 equals to I naught equals to I reference upon 1 plus 2 by beta. The caution is that you will say ma'am was saying that it's a current mirror. Both current should be same, but here it is not same. There is some factor of beta. So current is same, that is the ideal case. What happened ideally value of beta is very high. Okay, ideally value of beta is very high. Very high means we can say it's infinity. When you will put in this equation, what is I naught? I naught equals to I reference upon 1 plus 2 by infinity, and 2 by infinity, something divided by infinity is 0. 1 plus 0 is what? I reference upon 1 plus 0. 1 plus 0 is will be 1. So from this equation your I naught equals to I reference. That is the concept of current mirror. But that is ideally. That is ideally. Okay. That is ideally understood. Oh, wait a minute. So what we can say, this IC2 equals to I naught ideally, but practically approximate because beta is almost high. So this was a concept using BJT. Now next topic is two transistor MOSFET currents. What is the difference between these two circuits? If you see here BJT and here MOSFET. If you have remember all my previous lectures, a normal basic concept. In the BJT there is some base current, but in FET the gate current is always 0. There is no gate current at all. So whatever current flowing at drain terminal, that the same current will flow in the source terminal. Okay. So the concept of current mirror is whatever current flowing is I reference, that current is equals to I naught. Okay. Now it's a MOSFET and the equation of MOSFET are different. Now you can differentiate it's enhancement type MOSFET, not the depletion type. And for enhancement type MOSFET, if MOSFET is working as an amplifier, it works in saturation region. As a saturation region, the formula of current is I equals to K. K is your device parameter. That is the value of K is, if you remember, mu COX into W by L. If it is NMOS, the L will be in suffix mu and COX, W by L for NMOS. Mu for mobility, COX for oxide capacitance, W is the bit, L is the length. Okay, so I reference equals to Kn 1 because we are taking for one MOSFET. VGS minus VT1 whole scale. Now we want to calculate I naught. Okay. So from this equation you can easily calculate VGS because this 2 will this Kn1 will be in here in mid divide 1 and this will be under root and VT will be plus. Means simply you have to rearrange this equation, then you will get VGS equals to VTN1 plus under root I reference upon Kn. Okay. Now For same equation for I naught means for output current I naught equals to Kn2 VGS minus VT into whole square. Why we have put VGS? Because both transistors we have taken identical. Both transistors we have taken identical. Both VGS will be same. Okay. Now the both VGS is same. So what we will do? This is equation 1. Put the value of VGS from equation 1 to in this equation 2. Okay, means the Kn2 is same. Now value of VGS was Vtn plus I reference upon Kn1. So I reference upon Kn1 plus Vtn1 and minus Vtn2 whole square. Now again, as per current mirror rule, both current should be same I not I reference. That is the caution in your mind. But for ideal case, identical case, the threshold voltage are equal. If this is equal, this will be cancelled out. And under root n square will be cancelled out. So what will happen? I naught will be Kn2 I reference upon Kn1. If both transistor size is also equal, means width and length also equal, then Kn will be equal. And that case, I naught will be equals to I reference. I guess you got it. Again, listen carefully. This is the equation. But if this equation for ideal condition, this is equal and this is also equal. So I naught will be I reference. Simple. Okay, that is the ideal case. Suppose everything is equal but W by L is not equal, means the size is not equal. Then the Kn to Kn1 will not be cancelled out. So in that case, the formula will be I naught equals to Kn2 upon Kn1 I reference. And you know in Kn2 by Kn1, then Kn1 is mu n Cux, W by L for 2, W by L for 1, W by L for 2, and this mu n Cux, W by L for 1. But mu n Cux is a constant parameter, so what will be there? W by L2 by W by L2. So, okay, when your when your all parameters same, the current is same. But when all parameters same except the width and length ratio, then the formula will be this W by L2 by W L plus I difference. Suppose we are talking about the saturation current, means channel length modulation coefficient. If you remember the basic fundamental concept of MOSFET, then what will happen? In channel length modulation, the length shifted like this. Okay, if you want in detail, please go to the previous lecture, the working of this MOSFET. Okay, and that happens only in saturation region. So one parameter added, that is lambda. Lambda is called channel length modulation coefficient. Okay, the formula of current will be K and VGS may be to whole square, and one parameter extra added, that is due to channel length modulation. Okay, and that happens only in saturation region. 1 plus lambda to VDS. Suppose this term is added, then both sides it will be added. Then in the formula, it will be I naught upon I reference WL2 by WL L1 into 1 plus lambda VDS2 upon 1 plus lambda VDS. Okay, so 3 formulas. One is ideally, total ideally, everything same. One is everything ideally except W by L ratio. And the next is not only W by L ratio, channel length modulation coefficient is also there. Then these are 3 formulas. Okay. Now, output resistance. Resistance is, you know, voltage upon current. But our output parameters current. So what we are writing? We are writing opposite. 1 by R equals to I by V. Okay. Change in I due to change in voltage. So what is this? Means just take differentiation of I naught with respect to VDS. I will take VDS2 means in this parameter. If you differentiate in this del I naught upon del VDS2, what will happen? How to take differentiation? Now these all parameters are constant. Means Kn is constant, VGS2 minus VTN2 is constant, square. Now 1 is differentiation 0 and lambda 2 will be same into VDS2 differentiation is 1. Okay. So apart from lambda 2, this is again the formula of I naught without channel length modulation. So you can write lambda into I naught. Same here. Lambda into I naught. Okay. I guess you are confused. So again listen carefully. The formula of I naught is Kn VGS minus VTN whole square into 1 plus lambda into VDS2. Okay. So we want to differentiate this equation, del I naught divided by delta VDS2. Okay. This whole constant term will be as it is. Okay, because we are differentiating with respect to VDS2. So according to that, this whole term will be constant only. This term is there. So one differentiation is 0 and lambda into VDS2, lambda will be there and VDS2 differentiation will be 1. And it is the formula of I naught without channel length modulation. It is I naught into lambda. Okay. So 1 upon R naught equals to 1 upon R naught equals to, wait a minute, 1 upon R naught equals to lambda into I naught. So opposite R naught equals to 1 upon lambda into I naught. So that is the derivation of output resistance. Okay. Now reference current means, what happened for the improvement, what we are taking, we are again attaching one more MOSFET for the reference current. If you see this diagram here, if I already explained in starting, this is reference current. Here we have attached one resistance. Now what have we are attaching one MOSFET for the reference current. Okay. So its name is suppose 3, 1, 2, 3. Now how to solve it? Now whatever one, the current flowing here, I reference, same current is flowing here, the same current flowing. So current through third transistor same as a current through one transistor. So we have taken current through third transistor equals to current through first transistor. Kn1 VGS1 minus VTN1 whole square equals to Kn3 VGS3 minus VTN3 whole square. When you will solve this equation, you will get the value of VGS1. Okay, because what happened in the last derivation also, what we have done, we have calculated VGS1 from this equation and put in the second one. Same concept we are applying here. From this, we will calculate VGS1, then we'll put the in the equation of 2. Okay. Now how to solve it? Please pause the video for a minute. Take a notebook and try to solve this equation by yourself. Okay. What you have to do, you have to, means this is this kn1 will be here. Okay. Then this square will be like this under root. Then the square will be over. Then this VTN will be here. It please plus the VTN1. Like this, you have to solve. Okay. And check whether you are getting the answer or not. So from this equation, we'll calculate VGS1. So VGS1 will be, now Kn3 upon Kn1 will write W by L3 by W by L1. Like this, we have to put. Okay. W by L3 upon W by L1. Please manage with the writing. Okay. Okay. So this is your basically Kn3 by Kn1 under root. Okay. VGS3 plus 1. This is your one equation. Now, how to get this equation? VGS1 plus VGS3 equals to V positive minus V negative. Okay. Now see. Just tell me, what is this KVL equation? I mean, just think about this. What is the KVL equation here? V positive minus VGS3 minus VGS1, very good, minus V negative equals to 0. So this is your equation, same equation written here. While you will rearrange it, VGS1, VGS3 on the other side, the V positive minus V negative equals to VGS1 plus VGS3. This will be your equation like this. Got it? So this is the equation VGS1 plus VGS3 equals to V positive minus V negative. Okay, so this is equation number 2. Now put the value of equation 2 in equation means just put the value of VGS3 from equation 2 to equation 1 and check this is the value of VGS. Okay. Now what you have to do? you have to calculate the output current. The formula of output current is Kn dash. It's Kn dash, not Kn. See, the formula of Kn is, if you remember, mu n Cox W by L. Okay, but this term Kn, mu and Cox, you can write Kn dash. Okay, so Kn dash W by L, and the 2 is in the formula. In the saturation is I naught equals to Kn dash W by L. VGS2 minus VGN2 whole square. Now put the value of VGS2 from VGS1 equals to VGS2. Put the value of this. This is your equation 3. So put the value of VGS1 from equation 3 to equation 4. Then you will have the I naught. Okay. What you have to do? You have to put the value of VGS2 from this equation to in this. Suppose all the WIL is equal. Then what will happen? This is the for you. Do the exercise. Then the both current will be equal. If all the W by L are same, if all the VT are in, then you check, you will have the same current. Okay. Now, one numerical is there. Design a MOSFET current source circuit to meet a set of specification. Design means you have to design the circuit. Design means you have the all the parameters. All the parameters, you should have weight, you should have length of the transistor. Now see what is given. It is talking about this particular circuit. Means they want to design this circuit. Means you should have WL for third MOSFET, WL for first MOSFET, WL for second MOSFET. Okay. So V positive is positive supply is 2.5, negative is ground. Okay. And the Kn dash is given, not Kn. Okay. Kn dash means it is given, mu and Cox is given. Your mu and Cox parameter is given. There is no need. Threshold voltage given, a lambda 0 means channel length modulation term is not there. Means the current formula will be simply Kn VGS minus, VGS minus K, VGS minus VTN whole square, just you will put like this formula. Okay. But if channel length modulation term is there, then 1 plus lambda VDS term is there. So here channel length modulation parameter is not there, this term will not be there. Only you have to put this. Okay. Design the circuit, then I reference is 100, I naught is 60 microampere. Means they are giving the reference current, output current, and VDS to saturation voltage is 0.4. So simply what you have to do, as per the circuit, we have to calculate the W by L parameter for all the transistors. Okay. See, W by L parameter for second transistor. For second transistor, the formula will be I naught upon Kn dash by 2 VGS2 minus VTN whole square. Means simply rearrange the formula. I naught equals to your Kn dash W by L, 2 is also there, VGS minus VTN whole square. Okay. Now, we're talking about two transistors. This will be 2. So we want to calculate W by L2. So these all terms will be divided. So K and I naught upon Kn dash by 2 VGS to my VTN. So whole square, every parameter is given. I naught current given, Kn dash given, VGS to VTN given. Now for first transistor, this will be 1. Okay, this will be 1. So Kn dash is same for all the transistors, so 100 by 2. Now, but for first transistors, what is the difference? We are taking for first transistor I reference. Okay, for first transistor, the current will be I reference. For second transistor, current will be I naught. But for third transistors, your VGS3 will be different. Okay, again listen carefully. This is your circuit. So these two VGS are equal. VGS1 equals to VGS2. But for VGS3, we have to apply the KVL equation. What is the equation? V positive minus VGS3 minus VGS1 and minus V negative equals to 0. So for third transistors, what we have to do, we have to calculate the VGS3. But first to second, the VGS is same. That is given in the question. That is VGS is not given here. Okay, so we can calculate VGS. VDS is given. Saturation voltage is given 0.4 volt. So what is see, VDS saturation voltage we are talking about, that is given 0.4. Saturation voltage is VGS minus VTH minus threshold voltage. This saturation voltage is given 0.4. VGS is not given, it's okay, but VTS is given 0.4, threshold voltage is given 0.4. So now from this equation, what is the VGS? VGS will be zero point 0.4 plus zero point 0.4, it is 0.8. Okay, that's why we have put 0.8 here, VGS1 and VGS1, VGS2 both are equal, 0.8, 0.8. But for VGS3, we have to apply the KVL. So V positive minus V negative minus VGS. Positive supply is 2.5, negative supply is 0, and VGS1 we have calculated 0.8 here. VGS3 is 1.7 volt. Okay. So now for third transistor, the formula is for first and third transistor, we have to take this I reference. This current is for third transistor, for first transistor, and this I naught current is for second transistor. See here in the numerical, for first and third, we have taken I reference, and for second transistor, I naught is. Okay, and the rest is same. Okay, so this is the comment is the saturation voltage. I have already explained you. Saturation voltage is VGS is this voltage. Okay, now the exercise for you. Same type numerical, only the parameters is same. What parameter here? The negative voltage is not 0, it is minus 1.8, and positive voltage 1.8. Okay, so there is little bit changes of current expressions. The current value was here 60 and 100 microampere, but here the value is 0.5 milliampere and 0.1 milliampere. Means formulas are same, only we have changed the values. So just check, uh, do yourself and check the answer. Answers are also given here 1, 2, 3. If there is any doubt, then you can ask by writing in chat box. Okay. So keep learning, keep sharing. God